In the last video, we were checking out the different types of partial fractions, specifically the proper fractions, and we determined there are at a high level there are three types. If you remember, let me scroll up at the bottom, at the top. I mean, so we discussed that we had kind of three types of proper fractions, and we had parked the improper fractions for later. So let's kind of discuss the first problem or the first type of proper partial fractions, non-repeating linear factors in detail in today's episode. So today's episode and maybe the next episode, these two episodes are going to be focusing on understanding some of the nuances of solving proper partial fractions, type 1, linear factors, non-repeating. In this episode, we'll get some intuition about what's exactly is happening and how to structure it. And in the next episode, we'll take a live example and solve it. So let's jump in right away into this episode. Okay, just as a quick refresher, if you remember the very first episode, we had talked about what is a polynomial. And I'm just trying to borrow some of the concepts again to just make sure that the dots are connected. So we know that the polynomial is nothing but an expression which consists of many terms. Typically, it could be more than one term, then that's all is polynomial. And normally a polynomial is arranged in the descending order of the power of the x variable or whatever is the unknown variable. So we start with the highest power. If you see some of the examples here, we start with the highest power and then go in the descending order of the power. So basically the expression is arranged, or the terms within the expression is arranged from the largest degree to the smallest degree. That's what we kind of do in a standard form of polynomial. And the smallest degree, when I say, if you see, the smallest degree could be just a constant. For example, if you check out this last example, the smallest degree is constant, because a constant can be thought about as a term which is kind of multiplied by the variable x to the power 0, because anything to the power 0 is 1. So the constant can also be thought about as having a x variable to the power 0. So that could also happen. It is not necessary that each of the polynomial might have a constant, but it can have a constant. And if it has a constant, always in your head during the mental math, assume that it's kind of associated with multiplying by x to the power 0, or there is a term kind of x to the power 0 over here, right? You can assume that there's a power x to the power 0. So that's how kind of the intuition is. So if you see some of the examples of how the polynomial is arranged here, if you see this polynomial, it starts with the degree 3 and then 2 and then 1. So it's the smallest degree is 1 here. In this polynomial, the degree starts with 4 and then 2 and then 1 here again. The smallest degree again is x to the power 1, the last term. And the degree is 1, the term is x to the power 1, but the degree is still 1 here. And then another interesting thing is some of the terms could be missing. It's not necessary that when we talk about descending order, all the terms should be in the sequence of descending order. For example, if you see there is no x to the power 3 here, that term is missing. That could also very well happen. So it could be in all assorted formats. The only thing is it's going to be in a descending order, and it can happen that the last term might be a constant. And if it's a constant, mentally should assume that it's x to the power 0 kind of a constant. It's multiplied with that. That means the x still is present there. And that concept will help you solve the partial fractions. The notion of doing that mental math, of thinking about this polynomial in a descending order, will always help you, and we'll see that in the next few steps. Okay, that was a quick refresher on the polynomial. And we also have learned in one of the previous episodes what is a partial fraction. A partial fraction, I'm not going to get into the details, you can check out the episode, but in simple terms, a partial fraction is nothing but we start with a rational expression like this, rational expression over here like this here. And what is a rational expression? Is nothing but a polynomial, a ratio of two polynomials, one polynomial in the numerator and one polynomial in the denominator. That's what a rational expression is. So we have got polynomial here and we have got polynomial here. So when we say decompose into a partial fraction or solve for partial fractions, typically we start with a rational expression, which is a ratio of polynomials in this format on the left, which is in green color. And we kind of end with a partial fraction, our final solution. This is our final answer. And which is typically like this, which is a simplified version or decomposed version of this expression, broken it down. And while doing that, we might factorize it on the way, and we'll discuss about that. So basically we start with a rational expression, which is slightly complicated or all bundled together and put in together, and we debundle or decompose into simpler fractions, something like that. That's the whole construct of a partial fraction, starting with something on the green side on the rational expression and ending as a partial fraction. Okay, so that's a quick refresher again. Now let's see what's going on. So for a minute, right, to just get some intuition, right, let's do the opposite. Instead of going from a rational fraction or rational expression and solving it for the partial fraction, let's do the opposite, which is what we have been doing all along this time during our high school mathematics or higher grade mathematics, where we took this kind of expressions. We were given the partial fraction and we were asked to simplify it to get the things in the green color. So basically we were given a partial fraction and we were asked to simplify to get a rational expression. So let's try to do that for a minute. Let's slightly take a detour here and understand some of the nuances, and then we'll come back to the concept of a partial fraction to see what exactly is happening. Okay, so this is what we are doing. So for a minute, we are going to do the opposite to get some intuition. We are going to start with the partial fraction over here. Okay, this partial fraction. Okay, we are going to start with this and we are going to go in the opposite direction and we have to come towards this left side. So we are going to start with the partial fraction and we are going to end with a rational expression, which is what this is. So exactly the same thing that I've copied here, but in the opposite way. From instead of left to right, I'm copying it from right to left, and I've color coded in the color. So we are going to start with blue and we are going to end with green. And let's say what are we doing all along the way in different steps, and then let's come back to understanding how to solve a partial fraction. Okay, so now our objective is to simplify this partial fraction below, this one. I've rewritten it here. And the simplification is a very simple process, not much. Basically what we're going to do is we're going to cross multiply, right, whatever the term is, and find the common LCM and kind of expand the brackets and simplify the expression. If you take step by step, I've put it here for simplification, where you're taking this into the brackets and finding the common terms in x and the constants, and the denominator is just multiplied x minus 3 and x plus 1 from this expression, the common LCM. And then we slowly come and we simplify, we get here 8x by 4 and plus 12 by 4. And finally, when we simplify it here, focus on the last two steps. The simplified expression over here in the first hop is 2x plus 3 divided by x minus 3 and x plus 1, these two factors. And then to further simplify, we expand these brackets over here and solve for this. So these two steps, focus on these two steps, right? And then we'll see what's going on. So from here, starting from a partial fraction over here, we have arrived at these two steps, the last two steps here in green, in this way by simple modification, where we have this, and the final answer is a rational expression. That's what we kind of decided as the objective, to end with a rational expression. So this is what we did. Now let's take these things and understand what kind of is a partial fraction and how to start, because in partial fraction we are going to go backwards. We're going to start from here and we're going to come to this equation, a simplified decomposed expression, which is a partial fraction. But let's understand some of the steps that has happened in between, so that when we solve this partial fraction, it gives us a good sense of what are we trying to do and why are we trying to do that. Okay, now let's trace, or let's kind of put some key observations of what has happened in this particular problem solving so far. Okay, so what I've done is what I'm going to do is let's work backwards. What does that mean? We're going to work from this point all the way till we get the partial fraction and see what's happening in between those two steps. Okay, and for simplicity, I've copied this. So we are going to start with the rational expression. We are going to work backwards. So I've taken this final answer, the last two steps. If you see this one and this one is nothing but this last two steps. Okay, I've taken that, and we are going to come all the way to the partial fraction. So our partial fraction over here is this thing, that is what we started with, and we are going to arrive at that. And what I've done is, this is what we have it here in the blue color. And what I've done is I've just added two more modified steps, which I will explain why we are coming here. So what I've done is, we know we have to come till this point over here. And this is as good as, if there is a constant, like I've explained, it is as good as multiplying by the unknown variable to the power 0, x to the power 0, because anything anything to the power 0 is 1, so it does not really change. So we can always add a x to the power 0 here and over here also next to these constants, kind of multiply both the constants by an unknown variable x to the power 0, which in effect will give us multiplying by 1. It does not change anything. And this whole thing is nothing but a constant. And let's say in one of the modifications, I'm replacing this constant by a and b, where a is 9 by 4 and b is minus 1 by 4. And just park these two steps for now. It's slight spin-off on the same expression. So let's park this for now and then let's see what's happening. Okay, let's understand the observations of what's happening while we are trying to solve the type 1 linear factors in the non-repeating format. Let's see what's happening here step by step, and let's go slow so that we are able to consume what we're talking about and it stays there forever. Okay, what is the first observation? Denominator is same but in factorized form, and each factor is a separate term in the partial fractions. So let me read it again. Denominator is same over here. If you see, denominator is same, okay, denominator is same but in factorized form, and each factor is a separate term in the partial fraction. What does it mean? If you see, once you factorize this given term into this format, which we have learned in the previous episode about factorizing polynomials. So we have simplified this x minus 3 and x plus 3. The same terms appear in the final answer. If you see all the denominator in the blue color, let me just make some space here. If you see all the denominator in the blue color, it's the same denominator. So it's not changing. The only thing that is there is over here, the denominators, the two factors are together multiplied. On the right side of the partial fraction, these factors are broken down individual or separate terms. That's what it means. So if you see, this is separated. So this plus symbol kind of separates this term. So this one term, this term 1 and this term 2, because this plus symbol kind of separates that. So the same denominator is separated. The factors remain the same, x minus 3 and x plus 1, but it's separated out here. That's the first observation, okay? And that's after factorization, remember that. The second observation is all the factors in the denominator are linear. What does it mean? The degree of the unknown variable is x is 1 in the partial fraction. If you see, the given expression was quadratic where we had the degree 2, but when we factorized it because factorization was possible. Now over here, it's a simple combination of two linear factors. The degree is 1 here and the degree is 1 here. And in the partial fraction also, since it's broken down, the degree is 1 here and the degree is 1 here. So all the factors starting from this point after the factorization, all the way through the partial fraction, all the factors are linear in nature, meaning the power of x is 1 or the degree of x is 1 for each of the terms. Okay, that's what it means. That's second observation. Okay, let me just clean up this so that we can do more doodling. Okay, and now let's see what is the next observation. Okay, the next observation is factors are non-repeating after the factorization. Post factorization, if you see, for example, from here you factorized over here, and after that we solve for the partial fractions. So if you see from this point again onwards, post factorization, from this point onwards, all the factors in the denominator are non-repeating. For example, x minus 3 appears only once, x plus 1 appears only once. Even over here, if you see, none of the factors are kind of repeating, especially after factorization in the given problem, right? And that's the reason this kind of nature is called as linear factors, non-repeating in the denominator. So if you see the denominator, the factors are not repeating in the given problem, but after factorization, because you have to factorize that to understand that if the factorization is possible. Okay, that's one. So this is also done. And again, let me clear this because I don't want it to be messy. Okay, all right, what is the next step? So we're going slow so that we can consume it. Okay, what is the let's focus on the numerator for a change. Numerator is just a constant in the partial fraction in both the terms. What does it mean? Over here, it is just a constant. Okay, it's just a constant. Over here, it's just a constant in both the terms. Okay, this is like term 1 and this is term 2 because it's separated by the algebraic addition. Okay, and when we say constant, we have learned, so constant is as good as multiplying it by x to the power 0, because anything to the power 0 is 1. And that's why I told you that I've modified this equation and put it so that you can understand. So the numerator is constant, and we can assume that in the mental math, that when you say constant, it still has the x variable to the power 0. Okay, that's what it is mean. And obviously it has to be x to the power 0, because if you see the bottom in the denominator, the x has the power of 1. So we cannot put the same power or a greater power, otherwise this will become an improper fraction, and we know that we are only solving proper fractions. So the power cannot be more than 1, and obviously that's the reason it's 0. So that's another way of looking at that. Okay, that's another thing. And what is the next step? Let's see. Just give me a minute here. Let me clean this up. Okay, all right. Okay, so that's also is done and dusted over here. This also we understood now. And what is the next observation? Degree of the numerator is less than the degree of the denominator. And by the way, we know this has to be true because this is a type of a proper fraction. The same thing I explained. The degree of the denominator is more or greater than the degree of the numerator. And that has to be the case because we are solving for only proper fractions. Otherwise, it will become improper fraction. So this kind of another way of putting that in a different context. And now these last 2 points are very important. Okay, now let's focus on that and let me go more slower. We can also see the degree of the polynomial in the numerator starts with 1 degree less than the degree of the denominator. What does it mean? The degree in the denominator is 1 and the numerator starts with 1 degree less than this. So if it's 1, it starts with 0. Okay, and that's another pattern. So in the numerator, we are saying that the degree of the numerator is not only less, but it's starting with 1 less because it cannot be an improper fraction. And then it's continuing as the rest of the polynomial like we discussed, because the polynomial will have this degree in the descending order like we discussed in the opening statement over here. A polynomial will have the degree in the descending order, okay? And sometimes it could be just a constant because we don't want to have more term. And in this case, it is going to be a constant because the degree is already 1. So you cannot have the same degree. So the only thing that is left is x to the power 0, but that is associated with a constant. So we have a constant here, okay? So we can assume that it still is a polynomial in the numerator, but it's just a constant, or it's a polynomial with x to the power 0 and some number along with that, okay? So that's what this observation is all about. And this will come kind of come handy when we solve the problems, like how to think about that. So this also we discussed. And I think we discussed this also, where the polynomial in the numerator is arranged in the descending order, where the power of term decreases for each succeeding term all the way through a constant term x0. Basically what we are saying is we start with x0, but we don't have anything further to go down because we cannot descend from there because that is the last term. But it was a different case if at the bottom it was quadratic x to the power 2, we would have started with x to the power 1, which we will see in type 3 when we solve quadratic equation. But if you see the notion that in the bottom over here also it's in descending order, which starts with power 2, then 1, and then 0, which is x to the 0. And same way in the numerator, it starts with power 1, and over here x to the 0. So it's again descending, this is descending. And the same thing is continuing here, where we have in the denominator, we start with 1 and we come to the constant, which is x to the power 0. And the numerator will have 1 degree less, because if it's not 1 degree less, then it will become an improper fraction. Again, it starts with 1 degree less and goes all the way through constant. But since it's a constant, that's just one term here, okay? So that's another thing. Hope that's not confusing. And this is also done, okay? So now, let me clean up. That's the last step now. What are we trying to say here? Okay, we got all these observations of what happened between the steps above. And let's see where are we going with this, okay? Okay, the last step, okay? The last step is, so what is our objective when we try to find or solve for partial fractions? Our objective is to find these constants in the numerator a and b. So what does it mean? We have to apply all these key observations, and from here, we start from here, and when we end here, we will not know this all along the way. In this case, we know because we are trying to mimic some of the example and we already know the answer, but in real time, whatever is highlighted, we will not know. We'll have just this expression over here, and we have to come up with this expression here. So our objective is to find the constant a and b, meaning that how do you find the value of 9/4 and -1/4? So that is substituted by a and b, and that's the reason I put this for a intuition. So the whole exercise about solving a partial fraction is from here you come to this equation, you form this equation, and why you form this equation you understood because I've explained you all the observations of how type 1 works. And the whole purpose is, once you get this, what is that we need to do in terms of mathematical computation and adjustments to find the value of A and B and then plug it back here to get this part, and that is your final answer. So that's the whole exercise. So finding the value of A and B or C, whatever is that, for this kind of problems for type 1 linear factors non-repeating, and getting these values and putting it back here in this format is your final answer. And that's what we kind of learned here. If you see the final answer, this is the final answer, right? This is the final answer. This is what we need to get. But how do you know the value in the numerator? How do you find that, the A and B? That's what partial fraction is all about, and that's what we're going to learn here. If you see here, expressing rational expressions into partial fractions and finding these constants A and B below, that's what the whole problem is. We'll start from here and we'll jump into a model of factorization or factorizing it here all the way along the journey. And our final objective is, since we're going to express this partial fraction in this way, if you see here, our objective is what is the value of A and B and how do you find that, so that we get the final answer of solving this given rational expression into partial fraction. And that's the whole intuition. All these steps and all these observations will come handy when we apply this to a live problem in the next episode. So watch out that. Hopefully this kind of intuition was useful and not confusing. And this will give us a better sense when we start solving the problems. And I'll see you in the next video where we talk about solving a live problem for type 1 linear factors, non-repeating partial fraction, that is specifically a proper partial fraction. Stay tuned. I'll be coming back on the next episode.